Okay, welcome back to the continuation of the myocardial mechanism lecture. So we just spent a little bit of time going over some basic cardiac cell mechanics as well as their contractile elements and the differences between cardiac muscle cells and skeletal muscle cells and their similarities as well. So now we're going to be moving forward and talking a little bit more, so getting a little bit more in depth about the mechanisms of the heart itself as a whole. Okay, so whenever we talk about cardiac cycle, we're talking about two phases, one diastolic and two ejection. So we have a filling stage and we have an emptying stage. I like to say cycles per minute or cardiac cycle. I know we use the term a lot, beats per minute, but the word beat really just only gives credit to actually ejection. So actually when we talk about a cardiac cycle, we have to talk about diastole and systole as well. Okay, so let's first talk about what cardiac output is. Cardiac output is the product of heart rate and stroke volume. So that is heart rate times stroke volume is going to give us our cardiac output number. Our average heart rate is about 75 cycles per minute at rest. Like we talked about that last lecture, rest person anywhere between 75 cycles per minute at rest. Our average stroke volume averages about 70 milliliters. So this gives us our cardiac output of about 5 liters. Our total blood volume is actually about 5 liters per reference person. So at rest, we are actually circulating the entire blood volume at one time. Okay, so let's now talk about one section of that cardiac output. Let's start with stroke volume. Stroke volume is the amount of blood, so the volume of blood that is pumped out with each given beat or each given ventricular contraction. Right, so 70 milliliters on average is being ejected per beat at rest. Okay, so stroke volume is actually determined by two factors. How much blood is going to enter the ventricle during diastole is factor one. And two, how much blood is left in the ventricle following systole. So it's considered a residual volume. So after each beat or each ejection, we're still going to have a residual volume in that ventricle. We're not going to eject 100% of it. So those two factors are actually going to determine stroke volume. So stroke volume will also depend on how long diastole lasts. The longer it lasts, the more blood will be put in. That gives us our end diastolic volume. So the end diastolic volume is also determined by those two factors. Okay, so let's talk about end diastolic volume. End diastolic volume is determined by two factors as well. How much, like we just talked about, how much blood is going to enter the ventricle during diastole, so how much time do we have as well, and how much blood is left in the ventricle following systole, our residual volume. So again, after each ejection, we're still going to have a residual volume in that ventricle. Those two factors are dependent on time, right? So a time factor of diastole, and two, what is venous pressure, the gradient. So that's important. The average end diastolic volume is about 120 to 130 milliliters. Okay, so we also call this the preload. So end diastolic volume and preload, those two terms in the heart are pretty much interchangeable, and we're referring to volume at this point in time. So preload or end diastolic volume is pretty much, or preload is pretty much our end diastolic volume plus our end systolic volume. So end diastolic volume and preload are usually used interchangeably, but our end diastolic volume and plus our end systolic volume is ultimately what gets us preload. So an average person has about 120 to 130 milliliters of preload as well, or end diastolic volume, because we are adding our end systolic volume to that as well. Okay, so what is ejection fraction? Ejection fraction is the percentage of the end diastolic volume ejected as the stroke volume, which actually comes out to be usually reference person between 60 and 65%. That's why if we look, we have 120 to 130 milliliters of preload or end diastolic volume. 60 to 65% of that is ejected as the stroke volume. So that's why when we talked about stroke volume, we go back here, it's about 70 milliliters, right? So that's about 65% or so, and it varies from person to person. So that's why we still have end systolic volume. So we're still going to have, we're only ejecting about 60 to 65% at rest of that total end diastolic volume. So that means we do have a decent amount of blood left over in the heart. You know, we have anywhere between 30-35% of blood left in as our end systolic volume. Okay, so with end systolic volume, definition is this is the volume of blood that is left in the ventricle after systole, right? So we just talked about that. This is determined by, one, what is the resistance to ventricular emptying, so our afterload, and remember average afterload at rest is about 80 millimeters per mercury, so that is again to reference what's the pressure on the aorta holding that aortic valve closed is going to determine of how much blood you're going to get out, right? And two, ventricular force, which we're talking about here, the force of contraction. Right, so if we increase our ventricular force, we will increase our stroke volume. We will increase the amount of blood being pumped out because we are increasing our tension that we're generating in the heart, so it gives us the capacity to eject a larger amount of blood. Okay, so let's talk a little bit about ventricular pressure. When we are filling during diastole, the pressure in the ventricles is relatively low, right? It has to be low because the pressure on the venous side of circulation is relatively low. And the only way we can have movement through the tubes, just like all of the basic concepts and gradients we've gone over, in order to have movement through the tubes, we have to have a higher pressure on one side than we do the other to get movement of fluid through the tube. So there has to be a higher pressure on the venous side of circulation than it does inside the ventricle itself. So as blood goes in, it goes through the atria and actually splashes down into the ventricle. Okay, so now we're going to go over some mechanics within the ventricles itself. So we're going to talk about something called what's called an isovolumic contraction. This is where we get to a point where all of the valves in the heart are closed, right? So we will have an increase in pressure with no change in volume. So this is a point in time where we have completely came in, all of the blood has filled into the heart, and all of the valves are closed. This is going to give us what's called an isovolumic contraction. So this is where calcium comes into the cell and we start to compress, right? Because remember, calcium enhances contractility, but all valves are closed. So right now we're generating a lot of pressure because we need a big pressure in order to open up those valves so we can eject out. So we keep compressing until the pressure in the ventricle exceeds the pressure in the aorta. Remember, we have to overcome that afterload in order for that valve to open for us to eject blood. So we have to surpass that 80 millimeters of mercury. So as soon as the pressure is greater in the ventricle than in the aorta, we will have rapid ejection. It's what's called rapid ejection, where blood exits the ventricle into circulation. We'll continue to squeeze so the pressure goes up some, and then the pressure goes up into the aorta simultaneously. The exits valves open and volume moves down, right? And then we'll have a slow ejection. So look at this diagram over here. This diagram is very important. So when we're talking about heart mechanics. So right here at point D, we have, this is a point in time when we have all valves are closed, okay? Right? Because we have an increase in ventricular filling. So volume is down here and then pressure is over here. So we have an increase in filling. So we can tell that all the valves are closed right there because we are increasing the amount of volume that's coming in, right? And then all of a sudden we fill to a point and then we start to compress. And then at this point, we have rapid ejection. Here's our isovolumic contraction right here because we've compressed, and right here we increase the pressure right here. Sorry, just to reference D, we actually have our valves are open right here, right? And our valves are closed at A, right? Because this is where we're increasing pressure with no increase in volume. So at D, we have our valves open. We know we have our valves open because we're filling, right? So our ventricles are filling at this point in time. Okay. And then we know our valves are closed here, right? So we close because we are not filling anymore. So we have no increase in volume. But then now the valves are closed. So now we have all this blood inside the heart. So we have a dramatic increase in pressure. So here, right, we have all valves are closed still, right, because we're not filling or ejection at this point in time. But the pressure gets to be so great, right? So we're increasing the pressure with no increase in volume. This is considered right here. You can see at A is our end diastolic volume. When we increase this pressure, we're going to exceed the afterload pressure, right? Left ventricular pressure. We're going to exceed that aortic pressure, and we're going to have rapid ejection, right? So this is going to be our stroke volume right here. So now at B, this is a point in time where our valves are going to open because we have exceeded the pressure we need to in order to open those valves, and we're going to rapidly eject blood into our system. Okay, so if we want to define isovolumic contraction, we know this is a point at where all valves are closed. It's where within the heart there's a dramatic increase in pressure without any increase in volume. So right here our valves have shut after ventricular filling from D to A over here, and then right here this is our isovolumic contraction where we have a dramatic increase in pressure within the heart without any increase or change in volume. Okay, so after we have our isovolumic contraction, we open up those heart valves and eject blood out into the system. We're going to be at C over here. This is also going to represent where end systolic volume is. Okay, so this is when we have pressure starting to drop. Okay, this is the first part of diastole, and then we start to fill again down here once those valves open at D down here. And then it'll come down and hit the ventricle again. But here we have the valves close again, and this is where the heart relaxes. We have that, what's called an isovolumic relaxation. Okay, so let's recap and go over this whole diagram right here and what it means with regards to ejection, filling, contraction, and all that within the heart. Okay, so let's start with D to A over here, down along the bottom over here, right? Again, volume is left ventricular volume we're talking about over here is along, and volume is along the x-axis over here, and along the y-axis we have pressure. Okay, so from D to A, it's considered ventricular filling. As blood fills the left ventricle, volume increases with barely no increase in pressure, right? We don't see an increase in pressure here a little bit until the end. But so there's really no increase in pressure as much in what we're filling here. So valves are open there from D to A, and here's where they close. So here our mitral valve is open and end diastolic volume is increasing, right? So we started down here, and then now we have end diastolic volume down here as we close those valves. That's going to be the amount of blood, the total volume of blood in the ventricle that we have the potential of ejecting out. Okay, now let's keep moving on to A to B. So right here, A to B, right? So here, all valves have closed. Ventricular pressure dramatically increases, but volume remains unchanged because, again, those valves are closed. Now B to C. Right up here, we have our ejection period. Our volume of blood decreases dramatically within the heart because opening of that aortic semilunar valve has occurred, and then now we have the outward flow of blood, right? So we have overcome that aortic pressure, which is our afterload, right? Which is holding that aortic valve shut. We have overcome that pressure. The valve it opens, and we have a dramatic increase in blood flow into the system, right? That's considered our stroke volume right there. Now the last one, closing the loop, C to D down here, is our isovolumic relaxation period. This pressure decreases as our ventricle relaxes. So the pressure in the heart is decreasing as we relax. The volume remains the same as point C, right? Because our heart valves are closed right here at this point in time. Then once they open back up, we will fill again and continue this cycle. That happens each time we want to take in blood and eject blood. That's one full cardiac cycle going out. All right, so now we just talked about some myocardial mechanisms and pretty much talking about stroke volume and diastolic volume. We talked about a lot of volumes and pressure loops within the system. Next, in the next screencast, we're going to start talking about the second half of the cardiac output equation, which is heart rate.